Hello, class. For this review video, I'm going to cover questions 15, 16, and maybe 17. I'll see if we have time to squeeze 17 on this video. Okay, so number 15, it says there's a 2000 consensus population of Colts Neck was 12,331, and it's growing at 12% a year. So I see that 12%, and I immediately think rate, right, equals 12% as a decimal 0.12. And I know the formula for growth rate or growth factor is B equals 1 plus R. So B would equal 1 plus 0.12, or B equals 1.12. Right, and that's going to help us because if we have an exponential function, we need to know what A and B are. So we've just found B. The A is the initial population, which is the 12,331. So we know A, we know B, so we can comfortably write Y equals 12,331 times 1.12 raised to the X. Right? Now I used X and Y, they use the letter P and T. It doesn't matter, right? You could use P equals 12,331 times 1.12 raised to the T for time. Either way is fine. All right, so question A is done. Right, and again, your teacher might want you to write P for Y and T for X for population and time, and that's okay with me. All right, so A is done. Part B, it says graph this thing. Okay, well, let's graph it. So I enter the equation into my Y1, right? But when you're thinking about a window, think about it. My initial value is 12,000 and it's growing by 12% a year. So I'll start at maybe 0 and I'll go out, I don't know, maybe 10 years. And I'll start at 0 for my Y min. But for my Y max, I need a number definitely bigger than 12,000. You know, maybe I'll put in, I don't know, 30,000. And if we don't like it, we can always come back and make a change, right? And again, why did I pick 30,000? I wanted a number bigger than 12,000. I like to double the initial value, which is 24,000. Then I just added a little bit more to it. I press graph. And all right, it's not my best work, but this will work. All right. I'm not going to handwrite this, but on the review packet, I think they want you to kind of sketch this, and maybe you'll label the x-axis with the letter X, the y-axis with Y, or you might use P and T, for population and time. Whatever you want to do works for me. But you should label the graph and give me a couple of tick marks, okay? So B is done. Okay, part C. Use the model to predict the population in 2004. So 2004 is 4 years after 2000. So that corresponds to x equals 4. So I'm going to plug in 4 into this equation and I'll solve. All right, so here's the equation written out. I replace x with 4. I type this into my calculator. And I press enter, and it looks like we went from 12,000 and change to 19,000 and change. So the answer is 19,403 for letter C. There you go. Now it says use a table to figure out when we will double. All right. So if I go to my calculator and I press second window, that's table set, I want to start at 0, count by 1. Now I press second and graph, and you want to scroll down to see when do you get to double, right? If my initial population was 12,331, double would be 24,661, right? So when do we get to, it looks like somewhere down here, right? Around year 6. So it looks like our answer is somewhere between years 6 and 7. All right, so if we use year 7, we would say 7 years after 2000, which would be year 2007. Okay, so we should write the table out though, using these numbers for 6, 7, 8. So let us do that. So I rewrote my table over here on the side, right? So remember, this is X years after 2000, and this is the population. So we get to 24,600, somewhere in between year 6 and 7. So we'll use year 7. So at X equals 7 is equal to 2007. Okay? I think we can squeeze in number 16. I'm going to clear my board, and then we'll start fresh with number 16. Okay, so for number 16, it looks like we have some type of function that models how much blood, how much of a drug remains in your body after the injection. All right, where y sub 0 is the initial amount of the drug. So here it says, suppose that 15 milligrams is injected, so y sub 0 would be this 15 at 8 a.m. So the initial time is 8 a.m. How much is left 3.5 hours later, right? So this t represents time in hours. So from 8 to 11:30 is 3.5 hours. So for letter A, we have to add, substitute 3.5 hours in for t. So I kind of did that over here, right? So I will, instead of saying times x, right, this was the initial equation I wrote over here, we're going to replace x with 3.5. Okay, so this would be times 3.5. I know that's confusing because you have 0.35 times 3.5. So in the calculator, in the calculator, it would look something like this. 15 times e raised to the negative 3.5 times 3.5. I press enter, and I get 4.4, okay? So I'll write 4.4. Now think about the original question. It was how much of the drug is still left in the bloodstream at 11:30. So again, we started with 15 milligrams, and then after 3.5 hours, we only have 4.4 milligrams of the drug in the body. Okay, so again, I'll just write here 4.4 mg for milligrams. Now it says find the half-life. Well, remember, if we start with 15 milligrams of the drug, half of 15 would be 7.5. So in the future, you're going to have half, which is 7.5. But we don't know the time. The time is what we don't know. Okay, so we have to solve this equation for x. So I think we should just graph this thing. Graph both sides of the equal sign and solve for x. So I'm going to graph y1 is 7.5 and y2 is the right side of the equal sign. That looks like this. Right? Left side of the equal sign, right side of the equal sign. And we're solving for x. So let's just make sure our window's good. 0 to 10 is fine. And the y max I have at 20. So remember, we're starting with 15 and we're going down to 7.5. So I just need a number slightly bigger than 15 for my y max. I press graph. And the intersection is what we're looking for. Second, trace, number 5, enter, enter, enter. And it looks like 1.98. Okay. So in this case, x equals 1.98. Okay. And I believe that's in hours, right? So maybe you would say just under 2 hours. So for letter B, the answer is 1.98 hours. Okay. And then letter C says if another dose needs to be administered when there is approximately 1.3 milligrams of the drug present, when should the next dose be given? So again, you're going to replace the y now with 1.3 instead of half, right? So this was for the half-life, 7.5, but now we're saying, what if we say instead of 7.5, it's 1.3? Right, everything else stays the same. There should be a point there, times x. Okay, so it's 0.35 times x. This is my E. So when I bring out my calculator, whoa. When I bring out my calculator, I press y equals. I only have to make one change. Change 7.5 to 1.3. Okay. And let's see if this fits on our graph. I press graph. Let's see if the intersection happens. I might have to make my x max bigger if I don't see the intersection. Okay, it worked. Not my best graph. All right, and now if I press second, trace, number 5, enter, enter, enter. All right, it looks like I get 6.99. So 6.99 hours, right? So we'll call it 7, right? So in 7 hours, you should administer the drug, right? Here we end up getting x equals, I rounded to 7 hours, okay? So again, after 7 hours, you should administer the drug. And if you want to know the exact time, well, 7 hours after 8 a.m., right, is really what we're talking about. So I think that would be 3 p.m., okay? And that's your answer for 16C, right? So I think I'll stop here, and I'll do another video to cover problem 17, which is regression, and I'll answer some of these other problems on the next page as well. Thank you for watching.